Each year on the 5 continents, more than 1 billion Magnum ice creams are consumed. This dessert, celebrated for its contrast between a creamy interior and a crunchy chocolate coating, reaches over 100 countries and symbolizes a small everyday luxury. However, behind that moment of pleasure lies a chain of industrial processes and scientific controls that ensure each unit maintains identical flavor, texture, and appearance from the factory to the home freezer. Join us on an exhaustive journey through the inner workings of that production, from the reception of milk to export logistics, including flavor research, cold engineering, and rigorous microbiological quality testing. Certain ancient texts attribute the first ice cream to China 4 millennia ago, when mountain snow was mixed with milk flavored with fruits or rice. Although the principle was rudimentary, the key concept remains: stabilize micro ice crystals so tiny that the tongue perceives them as cream rather than as granita. Over the centuries, various cultures added sugar, eggs, honey, or alcohol to the mixture, seeking to lower the freezing point and improve texture. In the 19th century, the invention of industrial mechanical ice cream makers made it possible to produce homogeneous batches in large volumes, paving the way for global brands. Magnum, created by Unilever, debuted in Italy in 1989 with a clear premise: offer a premium ice cream within reach of the average consumer. The sensory technical development team set the goal of achieving an intense natural vanilla aroma and a Belgian chocolate coating containing 30% cocoa butter that would crack with a dry sound at the first bite without flaking off. Achieving this required several months of thermal adjustments, rheology studies, and temperature shock tests. Our visit begins in the early hours, when a line of tanker trucks parks at the receiving docks. Each vehicle has been sealed at its origin, and its temperature is monitored by GPS. The drivers connect sanitary hoses to the sealed fittings. 40,000 liters of fresh pasteurized milk are pumped into cooling jacketed silos, located in a room held at 4 degrees Celsius. In parallel, 50,000 liters of sucrose syrup arrive in stainless steel tanks. Ultrasonic level sensors and magnetic flow meters verify that the volume received matches the order. The SCADA system records pH, density, and temperature. Only if all parameters are within range is unloading authorized. The milk provides proteins, caseins and whey, lactose, and fat. The latter acts as a microscopic lubricant between ice crystals. If its proportion drops, the ice cream hardens. If it soars, the mouthfeel becomes pasty. Therefore, it is kept around 11% fat content. Additionally, total solids are adjusted to 37% to ensure elasticity and resistance to melting. The syrup, for its part, not only sweetens, it also lowers the freezing point and acts as a natural antifreeze, contributing to creaminess. In a positive pressure white room, operators precisely measure the milk, cream, emulsifiers, mono and diglycerides, and stabilizers, carrageenan, alginates, or guar gum, depending on the recipe version. A paddle mixer turns slowly to prevent accidental air incorporation. The vanilla extract, sourced primarily from Madagascar and Papua New Guinea, is added in the liquid phase. Beforehand, it has been concentrated in ethanol for months to amplify its aromatic potency. Gas chromatography analysis confirms the free vanillin concentration and prevents adulteration. The mixture first passes through a plate tubular pasteurizer, where it is held at 84 degrees Celsius for 25 seconds. This treatment eliminates pathogenic bacteria such as Salmonella or Listeria, monocytogenes, without denaturing the proteins. Immediately afterward, a heat exchanger reduces the temperature to 4 degrees Celsius. Upon exit, the emulsion enters a 2-stage homogenizer operating at 150 bar. The first valve fragments fat globules from an average diameter of 3 micrometers to roughly half a micrometer. The second redistributes the fat phase among the milk proteins, creating a stable network that will withstand subsequent freezing. 10 metric tons of base are transferred to maturation tanks equipped with slow agitators. During a rest of at least 4 hours, the proteins hydrate and the stabilizers reach optimal viscosity. Every hour, a sample is taken. Viscosity is measured with a rheometer, freezing point, color, and acidity are checked. A panel of trained tasters samples small portions to detect sensory deviations. Only if the data remain within specifications does the batch proceed to the whipping phase. We enter the dynamic cold zone. The emulsion is pumped into the continuous freezer, a double-jacketed cylinder where ammonia circulates at 30 degrees below 0 Celsius through the outer jacket. Inside, a high-speed scraper blade removes the frozen layer forming on the wall. Simultaneously, a compressor doses sterilized air. The overrun level, the volume of air trapped in the mixture, ranges between 25% and 30% by volume, depending on the market. This parameter defines the lightness and the speed with which the ice cream melts in the mouth. A PID controller adjusts compressor pressure and shaft speed according to the internal temperature. The mixture, now with a mousse-like texture at 5 degrees below 0 Celsius, advances to the multi-lane extruder. Calibrated nozzles deposit cylindrical strands of exact volume onto a stainless steel belt. A high-frequency oscillating cutter sections each piece. A Delta robot inserts birchwood sticks, sterilized by steam, into the center of each portion. Immediately afterward, the belt enters a forced air freezing tunnel at 40 degrees below 0 Celsius. An algorithm calculates the belt speed so that the temperature gradient ensures simultaneous crystallization of the core and the coating. The average residence time is between 6 and 7 minutes. The chocolate arrives in 20-kilogram blocks. It is ground and melted in double-jacketed kettles at 45 degrees Celsius. Then, a programmed tempering process, controlled cooling to 28 degrees Celsius and reheating to 31 degrees Celsius, promotes formation of the cocoa butter form V crystal structure, responsible for shine and snap. A CIP, cleaning in place system, sterilizes the circuit between batches containing different allergens, e.g. nuts. The tempered chocolate feeds perimeter nozzles that create a continuous curtain. The ice cream at 18 degrees below 0 Celsius captures it in under 1 second. The thermal contrast solidifies the fat externally while the core remains stable. For variants such as almond or caramelized hazelnuts, the chocolate is mixed with roasted nuts that have passed through metal detectors. The resulting viscosity requires pumping at different flow rates. The machinery corrects its power in real time to maintain constant thickness. Every half hour, an operator extracts units and measures weight with a certified scale. A laser thickness gauge verifies that the coating falls within a margin of plus or minus 1/10 of a millimeter. The lab star color coordinates are also analyzed to detect deviations in cocoa roast. In case of variation above 2%, the line stops and a maintenance team inspects temperature, pump pressure, and nozzle calibration. Compliant bars proceed to the automatic wrapping station. A robotic arm groups them in tens and inserts them into metallized pouches with 3 layers: polyester, aluminum, and polyethylene. This sandwich acts as a barrier against light, oxygen, and moisture, preventing surface ice crystals. Next, 6 units are placed into an FSC-certified craft cardboard box. A laser printer marks the production date, lot number, and exact time. The shrink wrapper applies plastic film around 25 boxes and carries them through a heat tunnel that seals the film. An automatic palletizer stacks the bundles on sanitized plastic pallets. Full-aisle metal detectors inspect each pallet to discard any ferromagnetic fragments that could originate from machinery. In a warehouse maintained at 28 degrees below 0 Celsius, CO2 and humidity sensors prevent dangerous condensation. The WMS software assigns storage locations and generates labels with QR codes. Each code contains the complete production parameters: milk origin, microbiological analyses, tempering curve, date and time of each phase, and the serial numbers of the sensors involved. Thus, if a problem is detected in the future, the company can precisely quarantine the affected lots. For export, the pallets are loaded into refrigerated containers. Internal data loggers record readings every 5 minutes. If the temperature exceeds 20 degrees below 0 Celsius for more than 30 minutes, the system sends a satellite alert to the control center. Upon arrival in the destination country, the health authority can scan the QR code and access the full history. This transparency facilitates trade and reduces the need for duplicate sampling. The R&D laboratory works on project cycles of 6 to 12 months. For new recipes, technologists simulate chocolate cream interactions in 50-liter batches. They test versions with inclusions, cookie pieces, caramel, fruits, and adjust viscosity parameters, particle size, and melting point. Climate chambers recreate 6-week sea roots with temperature oscillations of plus or minus 5 degrees Celsius to simulate container openings. If the ice cream suffers burn or the coating loses its shine, the formula is not approved. In blind tastings, sensory judges score sweetness, aroma, texture, and snap persistence. 10-point scales and triangular difference tests detect minimal changes. Only combinations that exceed the reference average advance to a 500-kilogram pilot scale before industrialization. The plant has reduced its water consumption by 18% over the past decade by reusing waste heat to disinfect pipes and recovering condensate. Compressors use ammonia, a refrigerant with zero ozone depletion potential and low climate impact. Additionally, photovoltaic panels cover 14,000 square meters of roof and generate 2.1 gigawatt-hours annually, equivalent to the consumption of 600 homes. The cocoa comes from Rainforest Alliance certified plantations. Farmers receive training in pruning, shade management, and fermentation, which increases yields and quality. In return, the company pays a premium per ton invested in local schools and clinics. The wooden sticks are sourced from European forests managed under systematic replanting criteria. Each batch undergoes total aerobic bacterial counts and specific pathogen searches. Plates are incubated for 48 hours at 37 degrees Celsius. Meanwhile, the batch remains quarantined in separate chambers. With a negative result, it is cleared for distribution. The internal laboratory is ISO 17025 accredited and participates in annual interlaboratory proficiency tests. The quality culture is reinforced with ongoing training. Operators rotate among stations and conduct semi-annual technical tastings to keep their palate finely tuned. In this way, they can detect by sight or sound alterations that sensors have not yet flagged. When a lot falls slightly outside specifications, it is destined for internal markets with specific labeling or reprocessed into animal feed, minimizing waste. Since its launch, Magnum has expanded its portfolio. White chocolate, salted caramel, double layer, pistachio, and limited editions inspired by pastry desserts have emerged. Each innovation requires recalculating tempering curves, viscosity, and solidification time. The marketing department collaborates closely with R&D to ensure that exotic ingredients, matcha tea, freeze-dried berries, smoked sea salt, comply with allergen regulations and do not compromise product stability. Altogether, the Magnum enjoyed at home is the result of a complex chain where sustainable agriculture, process engineering, microbiology, international logistics, and sensory analysis converge. Each bite, that instant when the chocolate cracks and the vanilla begins to melt, encapsulates thousands of measurements of temperature, pressure, pH, and viscosity, dozens of visual and auditory checks, and the commitment of hundreds of people who, from the start to the end of the line, work to make the experience identical batch after batch, continent after continent.